information link?
No. Just, I don't need that. I don't need that. Yes, well, so we've done some job, I think not a too bad one, related to a very interesting phenomenon of the appearance of collective excitations in certain ordered systems as a consequence of deep theorems, such as the Postgraduate theorem, which dictates the appearance of gapless bosonic-like excitations every time a spontaneous symmetry of the Hamiltonian or Lagrangian or action, if you wish, as continuous symmetry of Lagrangian or Hamiltonian or action, gets spontaneously broken. This is not the only example, of course, because if it were only a single example, we wouldn't devote so much time to it. It's quite a general phenomenon. There are examples no less impressive than the phonons and crystals. And one of those is just the appearance of collective magnetic excitations, the so-called magnons, in magnetically ordered systems. You know that there are subsystems, physical objects, forming crystals, and the atoms have a very specific feature. The so-called D or F inner shells are filled partially, and there is a non-zero spin associated with each such atom. What happens next is, of course, the overlap of the electronic shells of the corresponding atoms. But since these shells are very deep, they're located not on the outskirts, so to speak, of the electronic cloud, but in the inner part of that. Therefore, the overlap is very small. As a consequence, the band, the D or F, the inner band, turns out to be extremely narrow, as opposed to, say, the convection band, which is formed due to the S or P orbitals. And therefore, in the zero-order approximation, you can simply think that these spins are well localized. The band delocalization, the degree of delocalization is so small that in the zero-order approximation, this is treated as localized. So you have a notion of a spin, which generally is a quantum object. You can associate the spin with the lattice point, lattice side. You may now consider another object, again spin, but localized at some other side, presumably not far away from the first, because if it's located far away, then they wouldn't talk to each other. Why? Because, as I already said, the wave functions of the corresponding deeply localized orbitals almost do not overlap. Right? I can put here some C function. Sometimes it's called the exchange integral, depending on the distance between these 2 points. And basically, being contributed mostly by the nearest neighbors, for the reason I already explained. And what remains to be done is to sum over m, and write down the Hamiltonian on this form. And this is a scalar product of these two spin operators. Well, you could have anticipated the structure without any derivation and without any calculation, even though it's a very, very interesting and deep quantum mechanical phenomenon, which you learn already when you study atomic physics. It's called the exchange interaction. This is something which is absent in classical physics. That's the interesting point. If you build up an interaction, if you build up, you consider electrons, say, orbiting about two different nuclei, say centers, like in helium, in the helium atom, for instance, right? Or well, in the hydrogen molecule, or you have two electrons orbiting about the same nucleus, but there are two electrons, and there is some interaction. In former and second cases, there are Coulomb interaction. If it were only a classical system, there will be simply Coulomb interaction, nothing spectacular. Quantum mechanics introduces something new, which is absent in classical physics, the so-called exchange interaction. This is actually the very thing which calls for complete revision of our understanding how identical particles behave, because this is the special, another symmetry with respect to the interchange of the interaction. So you may ask yourself, if you have two spins 1/2, as you perhaps remember, the spin 1/2 is described, the operator for the spin 1/2 is described by a Pauli matrix. The Pauli matrix here and here, I supply them with the indices 1 and 2, and then I can consider a system with 2 degrees of freedom labeled by 1 and 2, and then I would ask myself, is this with 2 degrees of freedom or particles? The spin degrees of freedom are simply interchange, how to build up the operator which does that job. So for instance, I can build up the wave function psi, sigma 1, sigma 2 for this system 1 and 2, depending on the spins, and I can define this operator in this way. I simply interchange these 2 spin variables. And then you can prove, it's a simple problem to show that such an operator, first of all, it has to be invariant under spin rotations, because the world is invariant under such rotations. Therefore, it may contain only 2 invariants, a constant term and the scalar product of 2 Pauli matrices. Why not higher orders? Because sigma 1, sigma 2 to any power n, when n is larger or equal to 2, reduces either to identity matrix, the product of 2 identity matrix, or the first power of sigma 1 and sigma 2. There are no more invariants, only 2 of them. Identity and the first power of this scalar. So all you need then to do is just to find these coefficients. There are several restrictions which help in this case. First of all, P12 square should be P12. It's a projector. It has the meaning of the projector. I'm sorry. It is not. It does not. This is not the projector. This is the interchange operator. Therefore, P12 square is 1. I'm sorry. Projectors come later. Projectors appear when you realize that the 2 spins 1/2 may be either in the state with the total spin s equal to 0, when s vector is s1 plus s2. And you perhaps remember that the values of the total spin vary from s1 minus s2 modulus and s1 plus s2. So therefore there are only 2 allowed values, 0 and 1. This is called a spin singlet, and the second is called a spin triplet. In the first case, the spin has only 1 projection, which is 0, which is quite natural. If you are 0, you project onto any direction, you get the 0. But when we have spin 1, then depending on the chosen spin quantization axis, you may have a projections plus minus 1 and 0. This is all you know, this is everything's fine, but it's absolutely clear that this spin rotational invariance, sometimes called SU2 symmetry, tells me that the eigenfunctions of these interchange operators must be classified according to the total spin, because the total spin is a good quantum number. So, therefore, there may be wave functions which describe a triplet state, and there are 3 plus minus 1, 0 wave function describing singlet state, the singlet state. And it is also well known that when you have a singlet state, then the wave function is antisymmetric with respect to the interchange of the 2 spin variables, because if you know alpha a speed up state and beta a speed down state, then this wave function which describes a singlet is simply alpha 1 beta 2 minus alpha 2 beta 1 square root of 2, whereas the 3 functions describing the triplet are alpha 1 alpha 2. This is the projector. Projection equals to 1. For the projections equals minus 1, I will have beta 1 beta 2, and the third is 0 spin projection. That is alpha 1 beta 2 plus 2 beta 1 square root of 2. So these 3 functions are symmetric with respect to the interchange, and this is antisymmetric. So this is total spin 0, this is the total spin 1. So therefore, this operator acting on these states doesn't change them at all, because it interchanges them, and these are symmetric. Whereas the same operator acting on the singlet state changes its sign. It's enough. Once you have this, and you have the structure and this condition, you immediately find out the coefficients A and B. So this is why I just gave you some kind of general flavor for this derivation. But I'm sure you already know. And the result is this interchange operator is 1 plus sigma 1 dot sigma 2 divided by 2. This is how the interchange operator for the 2 spin 1/2 looks like. It completely can be expressed in terms of the constant, which is 1/2, and the other is the scalar product. So that's the origin of this term, which appears here. So of course it reflects some kind of symmetry with respect to the interchange of the spin degrees of freedom. And then you simply have a generalization for the spin 1/2 to higher spins. In principle, when the spin is greater than 1, if you are a consistent theorist, you cannot keep only this expression. You have to have a polynomial when higher order, higher powers of this product will be present if S is greater than 1/2. But nevertheless, the simplest form, in the simplest form, this is known as the Heisenberg model. Heisenberg model. It's a complicated, and so far in its most general setting, yet unsolved problem. Its solution is known in certain physical limits, but the most complicated part is associated with possible phase transitions, which are described by this model. When you have many spins interacting via this term, this interaction, then one of the possibility, which you may anticipate, would be if I start with the high temperature, at high temperature, the thermal excitations of the spins dominate, which means that the entropy is entropy arguments are most decisive. The system is disordered, and the average value of the spin is 0. The spins can look in any direction on average, and there is no spontaneous magnetization. Whereas on the other hand, there is a tendency towards certain ordering, because this is the system which has a levels, and these levels, different values of the energies, depend on the ordering of the spins. For instance, if you consider the simplest model, just imagine that you close your eyes and consider the problem of two spins, and these spins are treated as classical vectors, just classical vectors, forget about quantum mechanics. What is the ground state? What is the minimal energy state in such case, right? Okay, since I have a classical vector and I have a scalar product, I have to minimize this energy, and the energy will reach its minimum, well, depending on the sign of this coupling constant. If this coupling constant is negative, then the larger is the scalar product, the better for the energy. In other words, the scalar product will support a parallel orientation of the spins. Whereas if this is when J is negative. This is the so-called ferromagnetic case, ferro. I may have also this kind of configuration. This would be correct when J is positive, and this is called antiferro configuration. Antiferro configuration. Please notice I can only indicate the relative orientations of the spins. But I cannot say anything about the direction along which the spins will be directed. Why? Because of the obvious spin rotation invariance, very much similar to what we have in crystals. We know that the crystals break translation invariance, that we cannot exactly tell where the crystal is located. There is a parameter B. You remember? You label the location of your atoms using the lattice spacing by labeling the lattice sites, and you also have a certain degree of freedom to make a shift. Instead of this shift here, it's proper to talk about rotations, global rotations. You have the sphere, and this axis, which is shown here, which specifies the direction along which the two spins will be directed. They will be parallel anyway, or anti-parallel. But what is the ultimate direction? The answer is any on the surface of this two-dimensional sphere, with the radius 1, so any unit vector and not would be good, because I would simply write down something like this. S would be a length of this vector, and not would be the unit vector, which specifies the direction of the sphere. And every time this happens, I would say, oh, this means that the ground state breaks this symmetry. But on the other hand, the ground state would be degenerate, because I can start rotating my arrow along any path on the surface of the sphere, and the energy is not going to change. Because the energy only depends on the relative orientation of the two spins, but not on the direction of this, so to speak, quantization axis. So you already start feeling analogy, right? With the case of forms. It is important to us to understand when and under what circumstances we can replace this picture, which is essentially quantum, even though I didn't say much about the quantum nature of this Hamiltonian apart from a few lines related to speed 1/2. Under what circumstances we can think of at least approximate applicability of classical physics? When the spin can be treated as classical. To do that, what you need to do is, first of all, you have to recall the algebra of these spins. Let us fix n fixed. In other words, we have chosen a point in space, we have chosen the lattice site, and there at this lattice site we have 3 spin components, Sx, Sy, and Z. Just don't be confused. Every time I'm talking about the components of the spins, this only makes sense if I have already chosen the quantization axis. And this choice is very much arbitrary. And very much like what we have in case of crystal, from which point I will start measuring the location of an atom depends upon me, or upon the choice of the reference frame. The same is here. So I find some, in spin space, I find some direction. Basically and predominantly, 99% of cases, this is of course some kind of magnetic field which directly acts on the spins, and therefore its direction fixes the natural direction for the spin composition. And then the x and y is more or less at your disposal. You may choose this one, or you may choose that one. Sometimes crystalline axes dictate you, okay, because of the spin orbit coupling or whatever. Anyway, so you have 3 components. Let us call them as alpha. Alpha taking 3 values, x, y, z. Very frequently, instead of x, y, z, we may write 1, 2, 3, which is just the same. And here comes the algebra. S alpha, S beta is equal to I, epsilon alpha, beta, gamma, S gamma. This is the algebra, the famous SU2 algebra. Which characterizes the dynamics, quantum dynamics of these objects. You can see that. This is a commutator, I have to emphasize. This is a commutator. And what is epsilon alpha beta gamma? Epsilon alpha beta gamma is the so-called Levi-Civita tensor. Levi-Civita tensor. It's the so-called absolutely antisymmetric tensor. Antisymmetric under interchange of any 2 indices, which means that for any 2 coinciding indices, it vanishes. And it takes the following values, E epsilon 1, 2, 3, and then you do a cyclic permutation, 2, 3, 1, 3, 1, 2, this is 1. And there is another value when you interchange any 2 of them, 1, 3, 2, and then again, cyclic permutation, 3, 2, 1, and epsilon 2, 1, 3, it is minus 1. So for instance, if you choose this is x, this is 1, and this is 2, the only component when alpha is 1 and beta is 2, what remains is 3, because all the others vanish, and so on and so forth. This is the SU2 algebra. It's a nonlinear algebra. The left-hand side contains 2 spin operators. The right-hand side contains 1 spin operator. Now imagine the spin operator is large. Not spin operator is large. Its eigenvalue, its maximum eigenvalue. Remember that if you consider the action of z component of the spin operator onto some state m, it gives you m times M vector, where M takes values from minus S to S, 2S plus 1. So there are two states. Is that there are two states, M is equal to S state. Sometimes they call highest weight states. So when S is large, when S, the magnitude of S is large, then typically the left-hand side is proportional to S squared, typically. And the right-hand side is proportional to S, first power. The commutator is of the second order. The right-hand side is of the first order in S, in large S. Right? So therefore, looking at this equation as a constraint upon the spin dynamics, you would say the left-hand side is much, much larger than the right-hand side. Roughly. Just forget it. Therefore, for large values of S, spin can be treated as commuting entities. Right? The larger the spin, the more classical it is. How can you understand it? If you take this value on the spin, the 2S plus 1 values of the spin, you can draw it using the following diagram. This is your value n equal to S. This is your value n equal to minus S. And now what you can do, you can draw that such picture. I understand you have seen it millions of times in your life already. If you're studying quantum mechanics, this must have been around. This would be n equal to S minus 1, because we can get the projection, n equal to S minus 2, so forth. This will be n equal to minus S plus 2. This will be minus S plus 1, and finally minus S. The semi-classical picture. In the old quantum mechanics, they used to use this representation. So when the magnitude of the spin becomes very, very large, the number of sectors becomes also very large, and instead of this, discrete picture, you eventually arrive at the continuous curve. And the continuous curve means that the momentum, the Z projection, the originally quantized Z projection becomes non-quantized, becomes continuous. That means classics. This is why it's a quite illustration why it should be classical. There is another argument, also quite nice. What remains in classical physics? In classical physics, there is no such a notion as spin. Spin exists only in quantum physics. But what do we have in classical physics? For instance, if we had an orbital momentum, we would say, oh, well, okay, orbital momentum can exist in classics. But there is a difference between the spin and orbital momentum, and the difference is this Planck's constant. If we want to build up something similar to orbital momentum, call it M, if you wish, it should contain H. Well, it follows already from the fact that the orbital momentum, if I define it as a vector product of the radius vector and the momentum operator, it has dimensionality, engineering dimension, whereas the spin is dimensionless. The spin is just a number. Now you remember what the correspondence principle tells us, the correspondence between quantum mechanics and classical mechanics. If you close your eyes without thinking much, look at the equations. When h goes to 0, this is believed to be the classical limit. Right? I'm against such treatment because there is no such a thing like sending a quantity which has a non-zero dimension to 0. You can't. You have to divide it by something, make it dimensionless, and only then you can send the result to 0. Only a number can be sent to 0, not the quantity which has a dimension. Right? So it's a good example of this kind. But nevertheless, if the momentum, if the spin is pushed towards infinity by hand, it's a quantum notion. This quantity must make sense in classics, so it must be measurable even in the limit when s goes to infinity. The only way to save the situation to send h to 0. This goes to infinity, this goes to 0, the product remains finite. And then this remains finite and has its counterpart in classical physics. So therefore, large S is associated with Planck's constant formally sent to 0. This is why it's a semi-classical limit, okay? Because you must be left with something in classics which makes sense. If you are left with nothing, if your spin disappears on the classical limit, this is not the correct correspondence principle. All right, so this is quite important for us to remember. I wanted to, therefore, to assume, first of all, that the spins are large, and what we have at our disposal is a classical Hamiltonian, which I can rewrite as a classical object. I can rewrite them in the following way. That will be sum over lattice sides n. G is the nearest neighbor. J goes outside, interacting. Only nearest neighbors are interacting. That will be Sn dot Sn plus G. I will specify what G is. Imagine that you have a cubic lattice, so you have a central side n equal to 0, and then you have a side a n plus n ax. This would be a n plus, let it be n plus ay. Correspondingly, this will be n plus az. So these three vectors, G takes values plus minus ax, plus minus ay, plus minus az. Here I showed only one direction, but there is a symmetric point on the other side along the same axis. So 1, 2, 3, 4, 5, 6. In three-dimensional case, you have 3 nearest neighbor for this cubic-like lattice. If you have a two-dimensional lattice, the number of nearest neighbors would be 4. In one-dimensional case, there are only 2. In d-dimensional hypercubic lattice, the number of nearest neighbor sides is 2d. So this is why what I'm writing here, it's just the scalar product between a given side at the point n and all its nearest neighbors. Now, an attentive student would notice that if I take into account the interaction between n and n plus ax, the interaction between this and that, and minus n, should not be taken into account if I'm summing over n. Is it clear? Just to avoid overcounting. I should take into account each pair once. Or otherwise I'm working with a doubled coupling constant. So to be quite accurate, I should put 1/2 here. Or simply say that this is not summation over n and g, but summation only about fixed nearest neighbor pairs, whatever. It's up to you to choose the way you prefer to do. Well, again, if J is positive, this is anti-ferrocoupling. If J is negative, this is a ferrocoupling, meaning that in the first case you prefer mutually opposite orientation of the spins. In the second case, you have a parallel orientation of the spins. You have many such lattice sites. Then there is a special requirement that in the antiferromagnetic case, your lattice must be bipartite, which means that your lattice must be divisible, or divisible is the right pronunciation in English, I don't know, in two sublattices, two independent sublattices. For instance, the square lattice, for instance, the cubic lattice as well. The square lattice can be represented as a sequence of A and B atoms forming two interpenetrating sublattices. This is one sublattice, the B sublattice. And what remains is the A sublattice, one into another. Now imagine that I put on A all the spins up, and on B all the spins down, and therefore what I have in the end is the alternating sequence of atoms, and this is what is called the Nersesyan, the state of which was conceived for the first time by the French physicist Nernst. Since after him, we call this configuration a Nersesyan. It's a classical picture. This corresponds to antiferromagnetic case. In the ferromagnetic case, when all the lattice sites are more or less equivalent, and what you have, it's a parallel orientation of all the spins. This is what the energy wants. This is the picture origin coming out from the energy consideration, from minimizing the energy. And of course, it cannot be decisive, it cannot be final, because, as I said, if I increase the temperature, you should think not in terms of energy, in terms of the free energy instead, because the entropy must be taken into account, entropy effect. And then it turns out that this picture must be destroyed at sufficiently high temperatures. No long-range order of the system should exist. And it will be very much similar to what we have in lattices. The lattice, as a lattice at sufficiently high temperature, melts necessarily. And there is no crystal anymore, it's a liquid. So something similar happens here with the spins. But since there is a tendency towards ordering originating from the energy considerations, there must be certain correlations between the spins. So in other words, you may ask yourself, what happens if at some point of space, at some lattice site, I fix the direction of my spin. And then I go in some direction, this is n, and then I go to n plus r. And this is some other spin, located at the site n plus r. And r is sufficiently large, much larger than the lattice space. And that means that I deviate further. And then ask yourself, what is this quantity? n plus r, which can be defined as n dot as n plus r. Well, the first more or less trivial thing, I would observe that in case of a ferromagnet, the result cannot depend on n. It can only depend on r because of translation relations. Right? So this function will be YAML of r. what kind of behavior can we expect? If we are in the ordered phase, then the correlations must be strong, so strong, that if you go at sufficiently large distances, in the limit when this distance, relative distance, goes to infinity, the right-hand side doesn't disappear. It's survived. By what? Here comes something you are supposed already to know from your course on statistical physics. Are you aware of the central limiting theorem? Central limit theorem? Perhaps you do. You are. Right? But quite physically, imagine that you deviate from this point by a very, very large distance r, which is much greater than the edge spacing. Whereas your interaction here spreads only within the first coordination sphere. It covers only, it takes into account only the coupling with the nearest neighbors. It's short range, extremely short range. And I'm going to very large distances. It's clear that if I go to the limit, when this distance goes to infinity, then the 2 points, these degrees of freedom, the spin degrees of freedom at very, very large points, become statistically independent. They do not affect each other to the extent as they would if they were very close to each other. No? So to be more accurate and more specific, if I carefully look at what is written here, it is called the correlation function. Averaging goes over all states of your system described by this simultaneous. This or that, classical or quantum, doesn't matter. The correlation function is what? The first term here, the spin here. I have 2 spins here, number 1, number 2. I am measuring the value of the second spin, which may be any, under the condition that I have fixed the value of the first one. In other words, this is nothing but the so-called conditional probability. It is not the probability per se. It's the probability under the condition that, and then I specify what is that, and what I mean. I want to know if I measure the value of the spin at this point, provided that I know for sure by 100% that the spin here at this point looks upwards. What is the value of that spin? So this is what correlations are about. How does the spin influence the dynamics of that spin such that under my measurement, the result measured here will be affected by the origin. And this operates as a local magnetic field, if you wish. This is what I'm asking, actually. If I apply a local magnetic field, because if I know for sure the orientation of the first spin, that means that it's under the action of some effective strong magnetic field, which fixes its value and direction. So how do the correlation develop? And what to expect? I will try to give you not a rigorous but vague, I would say, argument showing how one can proceed at high temperatures. How one can proceed at high temperatures. But for that we need to do 2 things. First of all, what is already been done. We are passing now to a classical description. The Hamiltonian is classical. But what is written there is a model which is spin rotationally invariant. It contains scalar product of 2 vectors. The spin is a 3-dimensional entity, a 3-dimensional vector which varies on the surface of the sphere. Let us simplify the problem. Let us kill the symmetry by hand. Exactly in the same way your colleague some time ago suggested that if I if I put my lattice into a, if I put under the action of, if it occurs under the action of some external potential, such that each atom is its own potential, well, then the Goldstone theorem should not work, because translation variance is broken, right? Imagine that in crystals there are such effects, that such things as magnetic or spin anisotropy. Out of all possible directions, for some special reasons of crystalline nature, quantum chemistry, the spin cannot deviate strongly from the given direction. It can be either along this direction or opposite, and nothing else. And this is called the uniaxial magnetism. Magnetism is characterized by extremely strong anisotropy. So that means that out of 3 components of my spins, only one remains, say Sz. And Sz is allowed to take 2 values, plus minus S, classical. Now, no one precludes me to do the following thing. To call that as Z is S, its magnitude, and sigma is a number, is a variable which takes 2 values, plus minus 1. And this variable is called the Ising variable. Well, the German would say Ising variable. But the English-American Anglo-Saxonian version is that Ising. I'm very proud of it. Ising. If you say Ising, also if you're German, it's better. Okay. I'm joking. All right, so if I now try to rewrite with some alternative in case of the so-called Ising model, then I would simply absorb GS squared into J prime, because this S squared will come out from there. And then forget about this prime, and I will be something like minus J, and sum over nearest neighbors, N and M, sigma and sigma. And now everything becomes very, very simple, because you have all the spins. You call the spin up plus 1, the spin down minus 1. And so you have a combination of pluses and minuses along the lines, and so forth and so forth. You can build up an enormous amount of configurations. And of course, with J, with the minus sign, if J is positive, with the minus sign, it is negative, it will favor the ferromagnetic configuration, or all the orientations of the Ising spins are just the same. And so forth and so forth. Now, we are talking about statistical mechanics, right? And statistical mechanics is described in terms of the partition function, so I have to sum over all configurations. This means that I have to take the sum over sigma 1, sigma 2, so forth, sigma n, and n is the total number of lattice sites. And write down exponent minus beta, beta is the inverse temperature, times the Hamilton. This is what is called the partition function. So once I know the partition function, well, in principle, I can also switch a magnetic field, which will look like this. But at this specific moment, I don't need it. But in principle, to take into account all the possibilities, I would need to switch on the magnetic field, to calculate, for instance, the magnetization and response, susceptibility, and things like this. And at the same time, I can also calculate any function, any physical quantity, any average. For instance, the correlation function, gamma r, which is the sigma 0, sigma r, which in this case would look like, here I would put z, and here I would put summation over all sigmas, sigma 0, sigma r, And the exponent, again, just the same exponent. H is, of course, the function of all the sigmas. So by this, I again assume summation over all spin degrees of freedom. But now here I have this quantity whose average value I'm interested in. And this is normalization. Right? Now please notice that if I have a summation over the spins, the sum over the spin with the spin sitting just inside this sum contains two values, plus minus 1. It's just 1 minus 1, it is 0. So the only thing which remains is this, which will give me 2. If I go to the second power to the square of this operator, it will give me this one. If I go to the third power operator, it will give me that one. So therefore, sum over sigma, sigma 2k is 2. Sum over sigma, sigma 2k plus 1 is 0. Trivial. Not a big deal. Now imagine that I have a two-side problem. I have only side 0 and side 1. The whole system consists of two sides. The total n, where is it? This n is equal to 2. I'm just interested in the average sigma naught sigma 1. So let's see what comes out of this. This average sigma naught sigma 1 is sum over sigma naught sigma 1, sigma naught sigma 1, and the exponent beta j sigma naught sigma 1 divided by the same, but without this term. Well, of course I can do this calculation exactly. There is no question about it, because each of these quantities are just as variables. But I want to prepare myself to a more complicated task. Therefore, let me consider the situation when the product beta times j, in other words, j divided by the temperature, is much less than 1. It's a small parameter. In other words, that's the limit of high temperature. So I have a natural energy scale, which is the exchange constant J, which gives me a typical distance between different levels of the system, right? And the temperature is much, much greater than this difference. It's a high temperature limit. And this limit you expect your system exposes the so-called paramagnetic properties. There is no ferromagnetism, that paramagnetism. On average, you should have 0. But because of what? We would like to see, because we would like to know the behavior of this function. So if it is like this, instead of this exponent, I will write down its expansion, beta j, sigma naught sigma 1 plus, okay, let me introduce gamma, which is the product beta j. It is gamma, which is much less than 1, and then I have O gamma squared, right? And here I would have 1 plus gamma, sigma naught sigma 1 plus higher order terms, or gamma squared. Okay. Well, this sum, the first term, it vanishes because of this. So the first non-zero term comes out from here. I get sigma naught squared, which is 1, sigma 1 squared, which is 1. Altogether I have what? In the numerator, I have 2 from here, another 2 from here, 2 squared, gamma. And from here, I have the lowest order term comes from the first term. It gives me 2 squared. Higher order terms, this vanishes. This will contribute, but will give me a higher order gamma square correction. Gamma square is small. So therefore, this is the end of the story. And the answer is gamma. Plus higher order terms. Is it clear? Right? This gives us a clue what to do when you have not 2 lattice sides, but you have a lattice of many sides. Suppose you have a lattice, but you are particularly interested in the following situation. This is your 0 side, and the side you are interested in, suppose this is the first side, and you call it the second one, and you are interested in this one, and you call it 3. And you want to calculate sigma 0, sigma 3. Next time I will push the 3 somewhere here. But I would like to see what happens here. Right? If I do this, now I will be vague, not precise in my words and in judgments, but I would like to convey the main principle. You see, I have a product of this and this speed, sigma 0, sigma 3. From my interaction, I may have, and I have an expansion of this minus beta h, this I will have times the speed, yes, and there will be something like A gamma and summation over n m sigma m, when m is any bond or any link which I can imagine on the lattice. The first link I need to what? I need to kill sigma zeros. Therefore, in this exponent, I should choose one of the sides coinciding with 0. But then this 0 should be coupled to one of its nearest neighbors. So in other words, I will have a gamma term from the one expansion of this exponent, sigma 0, sigma 1. This is fine with this, but it's not fine with this. Right? Because I will have to have, just a second. Yeah. Yeah, everything's fine. And the second step, I will choose the coupling between the first and the third sides, which is present in the exponent, and expand it, and throw out everything except for the terms which are present there. And now everything comes out nicely, because sigma 3 couples to sigma 3, and sigma 1 couples to sigma 1. So it's the minimal configuration, this and that, which allows me to reach this point starting from this one. I have an even number of spins on the way, on the path, such that every time when I square them, I have 1, and I have 2 to the power of something which is there. Right? Well, the numerator doesn't bother me at all, because it's basically, this term is decisive, the first one. All the others give me small corrections in terms of the gamma. Now it becomes clear that if I have a lattice, and I choose sigma naught here, and I take sigma r here, what I need to do is have to start from this point. Reach this point, go to the second bond, up, here, for instance, here. here, here, and here. With this path, every time I write down this length, I have a contribution sigma, gamma, sigma I, sigma j. But this is I and this is j. Every time. And every time each variable, Ising variable, will appear twice. Because otherwise it will not cancel. It will give me 0 in the sum. Now your natural question would be, what about other paths? Of course they exist. But the minimal paths, which I need to take into account, must have minimal length. Why? Because gamma will appear to some power of n when n is the length, some power of r when r is the length of this path. That is the number of those elementary paths which I need. I can choose another path when it comes here and then comes back, turns back and comes here, but that will give me a higher degree. And I don't need this correction. I need only the leading correction. Therefore, the problem sounds like follows. What is the number of all possible paths of the minimal length? What is the combinatorics of all this? And this number is finite, can be calculated. It will be some smooth function of R. But the most important part will be this. Because it simply measures the length of the trajectory which connects the 2 points. At high temperature, therefore, the only thing which matters is the trajectory of the minimal paths connecting 2 points, which depends with this combinatorics, of course, will depend on the geometry, on the type of the lattice, the type of the bonds, and it's important, generally speaking, but it's not crucial from the point of view that gamma to the power of r as exponent r of log gamma, and this is minus r to log 1 over gamma. So you see what happens. Gamma is small, 1 over gamma is large. And that's the main contribution, because all the others will give you a much less value of the correlation function. So, from this you conclude that your correlation functions, gamma of r, at temperatures much greater than j is proportional to some number, maybe even a function, smooth function of r, but not crucially dependent on that, exponent minus r divided by psi. Psi is 1 over the logarithm, 1 over gamma, right? Gamma was what? J, the t divided by j. And this is a large number, and this is a small number. If you want to install the true length, if r is not the number of lattice sides but length, then it must be multiplied by a lattice spacing, and this quantity turns out to be much less than a naught, which means that this information about what happens with the next spin, separated by the first by the distance r, gets at high temperatures, gets lost already on the distance of a nearest neighbor. You should not be surprised. Physically, this is a trivial result. At high temperatures, spins are completely statistically independent. They fluctuate in such a way they don't affect each other dynamics and the spectrum. So therefore, the distance, when they effectively correlate, turns out to be even smaller than the interatomic distance. It can be thought as being effectively 0. So it's a one-spin physics in this high temperature situation. But the very fact that this gamma appears is very important, because then you ask the next question. What if I release this condition, this restriction? What if I start lowering the temperature? Right? First of all, I can see immediately that psi becomes smaller. not as small as it was before. It may reach the distance of several lattice spacings. And moreover, the whole picture will become much more complicated because many more parts will start contributing. Not only gamma to the power, the minimal power, not only the minimal contribution, but also higher order terms will contribute. And nobody knows, so actually it's only an exact calculation shows what is the algorithm function. It's a problem of calculating these correlation functions, or most fundamental problems with statistical physics, because there are all reasons to expect that the system should approach the so-called critical point. The system will undergo a phase transition. And now you can understand what you should expect when you approach this phase transition. Why? Because looking at this formula, let me continue the argument I started talking about. In the limit, when r goes to 0, r goes to infinity, the two spins, whatever is the temperature, must become statistically independent in this limit. It's a central limit theorem, because this was looked as Sm dot Sm plus r. Correlations should start playing a role. Right? But now, the next step would be to say what? The system is translation invariant. This average and this average, in the case of ferromagnetism, if there is a magnetization, it should not depend on the point for a very large system. If it is an antiferro, then it will be some kind of oscillation. The result will depend on the parity of the sublattice or the parity of the lattice. But in this case, it does not. So therefore, it is S squared. At any point, suppose it's a 0 point. Doesn't matter. Translation variance. So, what can be the right-hand side? If I'm looking at this calculation, I see that the temperature is high, the right-hand side must be 0, because we have found the correlation function when r goes to infinity. Decays exponentially, falls out exponentially. So at large distances, the finite correlation length, whatever it is, a finite correlation length, leads to the fact that the right-hand side becomes 0. This is the paramagnetic disordered phase, a phase which keeps the same symmetry as the Hamiltonian. The system is not yet ready to undergo a phase transition. But if you occur below a certain temperature, the right-hand side may appear to be non-zero. You will get a vector as average, which is some function of t, such that this function below a certain temperature Tc, this function f of t, behaves like this. And that is spontaneous magnetization. That's the onset of long-range order. If we were in the case of our lattice, we would say here we have no lattice whatsoever. We have a liquid. The lattice has melted. It's melting. When it's a temperature, it represents a liquid. And now below certain transition, the melting temperature, the lattice shows up as an organized periodic structure. Well, the subtle point is that the melting point is not the second order transition crystals, it's first order. But specifically, essentially, the physics is the same. The way it undergoes a transition is different from what we will be discussing. But it's still there. So the right-hand side, therefore, represents as a measure of the long-range order. And this is the magnitude of this long-range order, the order parameter, the magnetization. The correlation function goes to a finite limit only in the ordered phase. And this is the region when the system becomes, shows up collective properties, which we will discuss later on. Whereas at high temperature, it is not. So this is all I wanted to say on very general basis, not rigorously, but kind of illustration. Now let's get back to our direct business, and let us therefore consider essentially a quantum problem, a problem of a quantum ferromagnet, under the condition that the spins of the ferromagnet are large, such that the semi-classical description would be applicable. So our model is, let me eliminate write down minus j here. Minus j here. This the abbreviation, these brackets, triangular, means that these 2 points are the nearest neighbors. Sn. J is positive, minus j is negative. It's a ferro case. And the spin is large, which means that the classical approximation must be good, or semi-classical approximation. We expect quantum effects to be small, but it's even more subtle than we could expect. Let us assume that we are at the temperature which is much well below the so-called Curie temperature. So in other words, let us assume that at some temperature our ferromagnet undergoes a phase transition from a paramagnetic phase to a ferromagnetic phase, and then we bring this temperature down to very, very low, small values, very close to zero. We are far away from the phase transition, even though that region is very interesting, but this time we are considering ourselves in the vicinity of absolute zero. So therefore, the first question we would ask, what is the nature of the ground state? Well, we believe that it's all the spins up. Okay, all the spins look in the same direction, not so fast. So suppose I take two speeds, two quantum speeds, located at the point 1 and 2, which are nearest neighbors. And let me choose the direction z to be the quantization axis, at the same time to be the direction along which the spin rotational invariance is spontaneously broken. So I do assume that the ground state is ordered, right, below Tc. And the spins are aligned along a certain direction. But let me clarify the nature of this state, whether it's classical or quantum. Now, this can be rewritten as S1z, S2z plus. Now, at this point, I'd like to introduce such operators. Are you aware of these objects? The circular, raising and lowering operators. Linear combination of x and y. And you can choose, and you can prove that what is written here is equivalent to this. So this is a diagonal term because I have an action on any state M. So first of all, any state M is a state, in this case for two spins, is a state of M1 and M2. And every time I'm acting on the M1, I have M1 times M1. Right? But when I'm acting by S1 plus, say on M1, then the right-hand side is not proportional to M1. It's a raising operator. It shifts and gives me a certain coefficient here in front, which I'm not interested in at the moment, but gives me M1 plus 1. Whereas if I had the minus sign, it will be the minus sign. With the one restriction. Very, very important restriction. It's again the same semi-classical picture. This is the projection. M is equal as Z, M is equal to S. And this is M equal to minus S. Now, if I am somewhere here, this is some M, which is less than S, I can increase it by 1, I can decrease it by 1. But if M coincides with its maximal value, I can't decrease it anymore. In other words, if S1 plus is acting on S1, the right-hand side is 0. You agree?
Yeah.
Right. The coefficient which stands in front, perhaps you remember, it looks like S minus M, S plus M plus 1, and things like that. It's quantum mechanics. Open the book and you find this, something like this. What is important is that if the first term increases the component of the spin on the first side by 1, the second operator does the same in the opposite direction. It's especially transparent in the case of spin 1/2. If you have such configuration, you can find the term. Suppose you have a configuration down up. This is number 1 and this is number 2. And you act by this term. S1 plus will transform the spin down into spin up, and S2 minus will transform spin up into spin down. In other words, it will produce a mutual flip of the spins. Right? And this will do just the same. But if I'm acting only by this operator onto this configuration, it will give me 0, because I cannot further increase spin up. It's already its maximum. So one thing is clear. If I consider now a configuration of 2 parallel spins, whether 2 up or 2 down, or better to say, 2 spin projections as S or 2 spin projections minus S minus S. Both of the maximum with the plus or minus sign. Acting by this piece on such a state gives me 0. It's the famous selection rule of quantum mechanics. The conservation of the spin, you cannot overturn the 2 spins simultaneously. Right? Which means that this part only measures the spin. It tells me that it's acting on the state M1, M2. It will give me the eigenvalue M1, M2, and that's all it can do. It gives me just the value of the 2 spins in the given ordered state. But this term would like to make the move. This term would like to produce these spin flips. That means that these spins will start exhibiting some dynamics. So if I am therefore in the ground state, which is all the spins up, which means that all m's, the value of mj for j, 1, 2, so forth, n, is equal to s, which is the ground state, acting by this part of the Hamiltonian on this state, I get 0. The conclusion. For any quantum ferromagnet, the ground state is classical. It is not quantum. The quantum effects in the ground state are absent. Because acting by the Hamiltonian, on the ground state of a ferromagnet, I obtain the same ground state of a ferromagnet. In other words, the classical ground state is an exact eigenstate of this momentum, with the energy determined purely from classical considerations. only for the ground state. Once you go to excited states, then of course you may have one spin in this, one spin may have this configuration, the other may have this configuration, and this process start developing. In other words, quantum excitations are quantum. Excitations in the ferromagnet are quantum, but not the ground state. That's the distinctive feature of ferromagnets. And plus one more feature of the ferromagnet is the fact that in a ferromagnet, in the ordered state of ferromagnets, when the spins are aligned, time reversal is broken. We didn't touch these aspects, time reversal aspects in case of lattice vibrations, because they were meaningless. They were completely out of, not to the point, just to talk this aspect, because everything was just quite symmetric with respect to time reversal. Not here. If you have a spontaneous magnetization and non-zero magnetic moment, that means there should be some current already present, because you remember how you create the orbital moment. We already have written it. The orbital moment, or the magnetic moment, already in classics, is a vector product of the radius vector and the momentum. And the momentum is proportional to the velocity. And velocity changes its sign when time changes its sign. It's odd when the time reverses. So therefore, every time, or physically you can say the following. If you want to create a magnetization, what you need to do, you need to have an electron orbiting along some circuit. So experiencing more motion along the closed circuit. And the orbital moment will be calculated using the vector product according to, again, I lost it. I just, so where is it? Where? MRTP. We change T to minus T, M goes to minus M, because P goes to minus P. Of course, nothing happens to P. So, time reversal is broken. You remember the dispersion of the acoustic phonons? You do. We say that it is. I'm finishing, just don't worry about that. The dispersion was, omega was Sk. But the good question would be, what was the equation whose solution gave us such a spectrum? The equation, we know that equation, this was d squared minus s squared dx squared equals to 0. After fully transforming here, we would have omega squared minus s squared, k squared would be 0. Square here, square here. Why square? Well, it's a huge symmetry here, it's a Lorentz invariance here. But why squared? Because everything is time reversal invariant. Omega to minus omega, symmetry. K to minus k, symmetry. The right to left symmetry. In space, and t to minus t, time. This renders this equation to be of the second order. Now, in the ground state of ferromagnet, time reversal is broken. So you may have, in the left-hand side, you should have not omega squared, but omega, the first power. Because second power would be typical for an antiferromagnet. Why? We will discuss it later. But for a ferromagnet, when time reversal is broken, omega must be in the first power. Whereas the space homogeneity and isotropy, again, will give us something like k squared. As a result, you will get a spectrum of ferromagnetic magnets of this form. So it's a kind of modification of the Goldstone theorem to a non-relativistic case. It's a headache for those people who would like to dig deeper and better. But you must be happy because the next example will be antiferromagnets. And antiferromagnets are very much like acoustic photons. The spectrum is quadratic, everything is Lorentz invariant, and everything is fine. So that's all I wanted today. So we'll discuss next time how to describe dynamics, low energy dynamics of ferromagnets under the condition that the ground state is classical, and therefore only excitations emit in quantum. In the case of an antiferromagnet, we'll find out not only the excitations, but also the ground state turns out to be quantum. Okay, so I push this. This. Who is the boss? You are the boss. I push this.
Yes.